In a Planck Hertz experiment, an electron of energy 5.6 electron volt passes through mercury vapor and emerges with an energy 0.7 electron volt. The minimum wavelength of photons emitted by mercury atom is close to. So, what happens here? When an electron hits a mercury vapor lamp, light will be emitted out, photons will be emitted out. Okay. Now, initial incident energy is 5.6 electron volt. It comes out with 0.7 electron volt, that should be associated as kinetic energy. Kinetic energy. Now, minimum wavelength of photons emitted by the mercury atom is close to. So, emerges with an energy 0.7 electron volt. So, change in energy is 5.6 minus 7.7. So, change in energy is 4.9 electron volt. So, this will be h nu, but you want the wavelength to be calculated. So, 4.9 is equal to hc by lambda. So, lambda is hc by 4.9, hc by 4.9 electron volt. So, energy in electron volt that can be calculated. However, I have to convert this into meters later. So, that is 6.62 into 10 to the power minus 34 into 3 into 10 to the power 8 divided by 4.9 into 1.6 into 10 to the power minus 19 coulomb. Calculating this, you will get 250 into 10 to the power minus 9 meter, or that is 250 nanometer. Obviously, by looking at the things, option C is correct, but see, there is also a shortcut to this. So, change in energy is hc by lambda. If energy is given in electron volts, this is energy is given in joules. So, there is another method, shortcut. So, in electron volt means it is divided by E, then you will get energy in electron volts. Then it is hc by E lambda. hc by E lambda is what you are going to get. Likewise, you can calculate hc by E is 1242 nanometer divided by lambda is equal to delta E in electron volt. So, that is 4.9 electron volt. This is 1242 nanometer by lambda. So, lambda directly when I calculate, it will be 1242 nanometer divided by 4.9, that also gets you to nearly 250 nanometer. Either you can choose this method or you can go for this method. Answer is one and the same, which is option C.